Uh, so hi everyone. So today we will start our tutorial 11 tutorial. So for today's discussion, we'll be continuing uh, the topic, that is how to calculate, like if you how to calculate equilibrium constant by using different types of distribution of particles in the energy levels. So let me, before starting that, let me briefly discuss about the topics that we covered in our last class. So we have started from the discussion of how the Gibbs free energy is related with the partition function. Okay, so change in the Gibbs free energy at absolute at absolute state, that is written by delta G0, is related with delta E0, that is the change in internal energy minus RT ln multiplication over J QJM0 by Na by nu J, right? This we have derived in the previous class, right? So uh, this is the basically relation of changing the Gibbs free energy, how the change in Gibbs free energy is related with the partition function. And from the statistical points of view, we like also derive this equation, right? So delta G0 equal to RT ln K. So here the change in Gibbs free energy is related with the equilibrium gas constant. Then uh, we have basically compared these two, and after doing that we got the expression of the equilibrium gas constants, that is looks like this: K equal to multiplication over J QJM0. QJM0 is basically the partition function uh, at standard state. Since all these things, all this change in Gibbs energy and everything, we are doing it when the system is in standard state, that means at 1 atm pressure. So because of that, we are denoting all the changes by using a suffix 0. Okay, so QJM0 Na to the power nu j into e to the power minus delta E0, that is a change in the internal energy by RT. Okay, so this is basically the expression of the equilibrium constant. Now next, if we given with a reaction like this, x2 is dissociated into 2x atoms. So x2 is a molecule that is divided into 2x atoms. So in this kind of a reaction, we have calculated the equilibrium constant. So the form will be looks like this. So QJM0 Na. So this nu j is basically the stoichiometric constant. So first nu j was 2. So first case here, for this case nu was equal to 2, and this is for the product, and for the reactant case nu is equal to 1, right? So sorry, nu equal to -1. So this should be to the power is 2, and second is QJM0 by Na. This will be to the power -1 into e to the power minus the energy that is required to basically break this bond, x2 molecule bond into 2x atoms. So that energy, that dissociation energy basically is considered as the change in energy. So we are writing the delta E0 as D. So this is basically d by RT, right? So now the whole thing would looks like this: k equal to q xm square by q x2 m 0 into 1 by na into e to the power minus d by RT. Okay, this is how equilibrium gas constant looks like for a simple reaction. Okay, next we have discussed like this is basically this q0xm or q0x2m. This is basically the total partition function, right? So it includes both rotational, vibrational, and electronic and translation. Yeah, so all of these four terms are included into this partition function q, right? That means that means for each of this atom or molecule that is taking part into the reaction, we have to explicitly calculate each of the partition function, right? Just like let's suppose for x2. Okay, so for x2, since x2 is a linear diatomic molecule, right? So its structure looks like this: x something like that. So as it's a linear diatomic molecule, so that means it obviously has a translational partition function. Since it's a diatomic, so it also has the rotational, and if the temperature is high enough, it also has a vibrational partition function. So qx2 m0 would be the multiplication of all these three types of partition function. Okay, similarly for x is just a monoatomic uh, gas or something like that, element, something like that. So for that, the only contribution comes from the translational partition function, right? So qt, so qxm0 would be just qt. See, the only contribution comes from the translational part, right? So now if you write that the whole thing into the expression of k, the equilibrium constant k, so it would be looks like this: kt, k would be, this k is the Boltzmann constant, kt q x square lambda x2 cube. Qt is basically lambda by lambda, v by lambda cube. Okay, so I'm just substituting all of this thing here. So at the end you will get the expression like this: p0 by gx2. Gx2 is the basically what is that called, degeneration of the state. Okay, qx2 v lambda to the power 6x into e to the power t minus d by rt. Okay, so p0 basically comes from, since this whole thing is, we are considering this whole thing is in standard state, so we can write p0 equal to v0 by rt. So we can write v0 as rt into p0. Okay, so we are basically substituting this v0 here into this expression of this translational partition function, and after doing that we will be getting this type of expression for the equilibrium constant k. Okay, so now next thing what we have done, we have solved some complex problem like this. This is a relatively easy example where just only only disassociation is involved, where x2 is converted into two x molecule, x atoms. So next we have considered a more complex kind of a reaction which looks like this: B into B is equilibrium with C into C. So the stoichiometric numbers are minus A for this, minus B for this, and for this it was C, right? Now since we have got all the stoichiometric numbers, now we can write the equilibrium constant K like this, right? QCm by Na, this to the power C into QAm0 by Na, this to the power minus A Q0 Bm by Na to the power minus B, right, into e to the power minus delta E0 by RT. So this is the expression for the equilibrium constant capital K, right? Okay. So using this simple form, we have actually solved different types of problem regarding this, where like all kind of vibrational constant, rotational constant, their degrees of freedom, the type of molecules, whether it's a linear, whether it's a non-linear molecule. Depending upon that, you have to calculate the partition function for each of the molecules and atoms, and after doing that you have to substitute those expression here, and from there you will be getting the expression, the value of the equilibrium constant K, right? So this type of problem also we have done in our previous class. Okay. Now next what we have discussed, uh, so we know that delta G0 equal to minus RT by ln K, where K is the equilibrium constant. Now this is the expression. So from here, what we can do, we have calculated the change in for a reaction, we can calculate this change of Gibbs free energy, and from there we can calculate the K. Now there is also another method to calculating the equilibrium constant K, that is that we know delta G is also related with the enthalpy change, that is delta H minus T into delta S. Okay, so that means that if Gibbs free energy of a reaction is changed during a reaction is changing, so that means the enthalpy and also the entropy of the system is changing. So that means instead of calculating the change in the Gibbs free energy, if we can calculate the change in enthalpy and the change in entropy during the reaction, from that also we can get the value of the equilibrium constant K, right? So so for that we have taken an example, right? So let's suppose there is a reaction going in. Okay, so let's consider a reaction in equilibrium which looks like this. R is in equilibrium with pre. R is the reactants and pre is the product. Okay, so now in equilibrium we know, depending upon the temperature, the reactants and products are basically uh, basically attains Boltzmann distribution, right? Among the states, among the accessible state, right? So that means it looks like this. So let's suppose this is the energy state of the reactants. Sorry, the reactants. 1, 2, 3, 4, 5, 6. So at a particular temperature in equilibrium, the distribution of the particles, these are basically the energy levels. So at equilibrium, the distribution will be looks like this. So ground state will be have the most energy, then comes second, third, fourth, fifth. So the distribution will looks like this. This is for the reactants at a particular temperature, and for product, energy states, overall energy states will be a bit higher, the 0 point energy state. So it will be looks like this. This is the difference in the 0 point energy delta E0. And as you can see, since this is the reactants and this is the product energy level. So as you can see, since the overall energy states of the reactants is lower than of the product, so the overall population of the reactants is dominant compared to the product. Okay, so since delta E0 is positive, so the population in R is dominant. Okay, like this, since the energy, that means since the energy, the overall energy of the reactants are lower than the product, so that means it's the energy states of the reactants are much more accessible for the molecules, right? So because of that, these energy states are accessible compared to the products, and because of that, the number of the population or number of molecules distributed among the accessible states will be higher compared to the reactant, compared to the product. Okay, now there is also counterintuitive cases are there where the distribution may looks like this. So where what happens, it will be looks like this. Let's suppose one energy state is there, second energy state, let's suppose a bit higher. Okay, like this. Third energy state is like this. This is for the reactants, and for the products it looks like this. This is for the products. Okay, so what actually see, there is also delta E0 is positive, right? So what happens here, that here is that, so although the overall energy of the product is higher than the reactants, but still the energy density in the reactants is higher than energy density, like the density of states, not energy density, density of states in the product state is much more higher than the reactant state, right? So because of that, the total number of population in the product state is much more higher than the reactant state. Okay, so in product, in P, the density of state is higher, so since P has high density states, that results into high total population in P. Okay, so as you can see, so uh, since the density of state in the product case is higher than the reactant case, so because of that the total population is high, okay, in the product. These kind of counterintuitive cases will be there. Okay, now what we can discuss, so this number of molecule in product and reactant states is follow a certain rule. Okay, so let's suppose, okay, so before that, so we have basically started our discussion that from here is that, like, instead of changing delta G, if you know delta H and delta S, from that you can calculate the change in equilibrium constant. So how can you do that? So the change in, so here let's suppose you somehow using some experimental method like spectroscopy or something like that, you can calculate this distribution of energy states of the products and reactant molecules uh, in a reaction that is actually established in equilibrium. Now, after getting that distribution of the molecules and atoms, you can easily calculate the change in energy, that is the delta E, change in 0 point energy, right? That basically gives you the delta H, that is the change in enthalpy. And if you calculate the uh, distribution, uh, population distribution, the population distribution basically gives you the entropy, the change in entropy, delta S, right? Like from the products and to the reactants, right? So so that means from this energy levels, if you know the change in the 0 point energy and the distribution, so from that to quantity you can easily calculate the change in enthalpy as well as the change in the entropy, right? Okay, so now let's suppose somehow calculate the change in the ratio. So the ratio, so let's suppose NP is the total number of product and NR is the total number of reactants. Okay, so NP by NR, you can calculate the ratio of NP and NR in terms of the partition function. So for that, what you can do, let's suppose you first do the summation over the reactants Ni. N is basically the total number of molecules, so you only take the reactants R, so that basically gives you, if you do the summation over the reactants, then it will give you the total number of reactant molecules, that is denoted by Nr. So Nr, we can write it like this, right? So Nr, so we know that Nr by N is equal to, sorry, Ni by N is equal to e to the power minus beta Ei by Q. So that means Ni will be equal to N by Q into e to the power minus beta Ei. So that means this would be equal to summation over reactants N by Q into e to the power beta Ei. Okay, so that means the summation would be all the possible energy levels of the reactant molecule. So that summation will be looks like this: N by Q summation over R e to the power beta Ei, right? This would be enough. Similarly, this is for the reactant. Similarly, for the products, summation would be on the summation, the summation would be all the product molecule. Okay, so this gives you NP, that is equal to N by Q summation over products e to the power minus beta EI, right? On the products, NP into equal to N by Q into e to the power minus beta EP. This one we can write as N by Q e to the power beta ER. Okay, so we have already discussed, right? So energies looks like this, energy distribution. So these are the reactants and these are the products. So there is basically, these are the products, there is basically a difference in the 0 point energy delta E, right? So basically EP would be ER so EP would be basically E prime P plus delta E0, right? So because the total energy is shifted by delta E, so if we started with if we started from the energy that is leveled with the reactant molecule, then that term would be EP prime, right? So we can write this as N by Q into e to the power minus beta. So we can write it like this. So you can do, okay, we can write it like this. So EP prime, this we can write as EP prime. EP prime equal to EP plus delta E0. Okay, so EP prime equal to EP plus delta E0. This would be N by Q So this basically gives you the partition function for the reactants, this term, and this term gives you the partition function for the products, right? So now if you do the ratio of NP by NR, this gives you QP by QR into e to the power minus delta E by RT. Okay, so let me just discuss it briefly what I have done here. So uh, this is basically, first the energy states looks like this. This is the reactant energy state, this is the product reactant state, product energy state, and this is the this is the reactant energy states, and this is the product energy state. So their 0 point energy are basically uh, different basically. So the difference is written here by delta E. So that means that uh, if you want to start, like, we can write this change in this total energy as a shift by delta E0 from the ground state energy, right? So we can write EP prime as equal to EP plus delta E0. So total energy basically shifted by delta E, right, from with respect to the reactants energy. So by considering the fact, so first what we have done, we know that energy is basically in equilibrium. These molecules are all distributed in the accessible, like distributed using the Boltzmann relation among these accessible states. So what we have done here, so we have used the Boltzmann distribution function here. So NR is the total number of reactant molecules which distribution, so number of total reactant molecules expression looks like this. So for getting this expression, we have used this expression of Boltzmann distribution, and we have summed over all the reactant molecules. Similarly, for the product molecules, we have summed over all the product molecules, and here also using this Boltzmann distribution, we got the total summation of the product molecules, basically having this kind of a relation. Okay, now from here we are taking the ratio of NP by NR, which gives you this kind of a relation NP by NR. Okay, so now since we got the expression of NP by NR, so next step what we will do is that we want to write the partition function. We will write the partition function in terms of this we will write the equilibrium constant in terms of this partition function. We try to find out if there is a relation between these two equation is exist or not. Okay, so partition function k, we can write it like this: summation over j q j n0 by na. Nu j is the stoichiometric coefficients into e to the power minus delta E0 by RT. Delta E0 is the change in the 0-point energy. Now for this kind of a reaction, reactant, it gives you product that is in equilibrium. So for this kind of a reaction, we can write the expression of K like this: QP by Na into QR by Na to the power minus 1. Since here the stoichiometric constant is -1, here is +1, to the power minus 1 into to the power minus delta E0 by RT, right? We can write it like, certainly write it like this. Now from here, so K now looks like, if you just cut the Na, it will gives you QP by QR into e to the power minus delta E0 by RT. So as you can see, so these two, 1 and 2, there is a clear relation between 1 and 2, right? So from 1 and 2 we can write K equal to NP by NR equal to QP by QR into e to the power delta E0 by RT, right? This is the expression of the equilibrium constant K, right? Okay. So that means if we somehow calculate the ratio of the products, the population of the products and reaction molecules, the ratio of the population, so from that quantity we can calculate the equilibrium constant K, right? I mean that quantity is exactly equal to the equilibrium constant K, right? Okay, so let's now do example like this. Um, so let's consider the similar reaction. The reactants gives you the product and the whole thing is in equilibrium. So let's suppose for reactants has only single accessible state. Okay, that means QR is equal to 1. Similarly, for product has a large number of evenly closed levels, means energy level. So QR has a single level, reactance has one, the single level, and the product has evenly spaced energy levels that looks like this. Okay, and this is product, and their energy difference is delta E0, and these are their energy difference E. Okay, so that means the energy looks like this. Zero plus delta E0, E plus delta E, 2E plus delta E. So energies, the values of energy will looks like this. Now for this kind of a system, if you can calculate, so first what you need, first you need to calculate the partition function for both the reactants and the product. So for the reactants, QR, summation over J, Gj into e to the power minus beta Ej. This is the expression of the partition function for the reactant. So since there is only single reactants is there, so the QR is basically 0. So this energy is at 0 level, right? So to the power 0 equal to 1. For products, it will looks like this, to the power minus beta Ej. So QP will be equal to 1 plus e to the power minus beta E plus e to the power minus beta 2 beta E plus e to the power minus 3 beta E, and so on. It will go like this. Now from here, so if you can took the infinite geometric summation over all the terms, then it looks like this, 1 by 1 minus e to the power minus beta E, right? The QP, the product, what is this called, this product partition function. So this is the expression of the reactant partition function, this is the expression of the product partition function, right? So now the equilibrium constant K looks like this, then QR is, so we know it's QP by QR into e to the power minus delta E0 by RT. So QP is here, QP is here, basically 1 by 1 minus e to the power minus beta E, and QR is here 1, so to the power minus delta E0 by RT. So now K would be looks like, so if you do the series expansion of e to the power minus beta E, it will looks like this, 1 minus beta E plus by one is like absorbed into this whole expression, so delta E by E0 by RT. Now for high temperature, okay, so we can ignore, so for high temperature beta would be very small, so we can ignore the higher order beta square or beta cube, we can ignore. So we will consider only the first term, that is up to the beta E, first order term. So in that case the whole expression will be looks like this. So for t greater than 1, that means beta less than 1, so that means this whole expression will be looks like 1 by beta E into e to the power minus delta E0 by RT, or it will be KT by E into e to the power minus delta E0 by RT, the equilibrium constant K. Okay, this will be the expression of the equilibrium constant K, right? Okay, so So we got the equilibrium constant K value. So so that means, so qualitatively what we can see is that the value of this equilibrium constant is depend upon whether the whole reaction is endothermic or exothermic, right? So whether the heat is generated or heat is absorbed during the reaction. So depending upon that, this value of delta E0 is dependent. This is specifically the sign of delta E0 is basically dependent on whether this reaction is exothermic or endothermic, right? So qualitatively, that property will be will be a major deciding factor of the calculation of this equilibrium constant K. The next thing that is also very important is how the population is distributed, right? So that in general, that is in general decided by the temperature, right? So depending upon the temperature, uh, the population in the energy states will be decided, right? So like if the temperature is very high, so that means the molecules or the atoms can occupy the higher level energy states. Right now, if the temperature is small, then mostly the particle will be or the atoms molecule will be occupying the lower level energy states, right? So temperature also plays a very minor role here qualitatively. So these are the two basically factors that uh, basically affecting the value of the equilibrium constant K, right? So K equal to KT by epsilon into e to the power minus delta E0 by RT. So if so that means if delta E0 is plus VE and very high, so that basically results into a very low value of K, right? Low value of K, right? So delta E is if higher, so that means KT by epsilon into 1 by to the power delta E. So 1 by 1 by e to the power delta E by RT. So denominator will be get higher. So overall the value of the term will be getting smaller. Okay, so that means if delta E0 is positive and it's very high, then we get a low value of K. Similarly, if delta E0 is plus V but small, then we get relatively high value of K, right? So that means that the value of the delta E0, whether it's positive or negative, that will significantly affect the value of the equilibrium constant K, right? So this is like this is how we can qualitatively predict how the equilibrium, how relatively the equilibrium constant K will change if we change, if we if we know the energy difference between the 0 point energy levels. Okay, now next thing we'll do a problem. Okay, so the problem will be uh, based upon a specific heat. Uh, problem is on basically in specific heat. So problem looks like this. Calculate the vibrational contribution to the molar heat capacity CV of carbon monoxide gas, assuming its vibrational wave number, that is a normal mode, is nu tilde equal to 2143 centimeter inverse at temperature equal to 800 Kelvin. Okay, so now, so for this problem, so that means for carbon monoxide gas we have to calculate the vibrational contribution to the specific heat. Two things are given. So there is only a single vibrational mode is there, that is the nu tilde, and that since that vibrational mode frequency, or not a frequency, the wave number is given 2140 centimeter inverse, and the temperature of the experiment is given 800 Kelvin. So what we have to do first is that so let me first write the all the mathematical expression that we know, that is that basically relates the specific heat with the partition function. Okay, so we know the specific heat at constant volume looks like this: CV equal to minus del U del, sorry, plus del U del T at constant V. This is nothing but C. So so in the problem it says that a molar heat constant, so that means you have to calculate CVM into Na, right, delta E by, so molar means molar means the specific heat of 1 mole of carbon monoxide, right? So let's suppose each of the carbon monoxide atom molecule has an average energy delta E, right? Now for 1 mole of carbon monoxide molecule that consists basically Na numbers of molecules, so that has the total internal energy U equal to Na into E, right? If this E is the average energy of each molecule, then for 1 mole of carbon monoxide the total internal energy would be Na into this angular bracket T, the average energy of each molecule. So that means it would be the CVM will take a form like this: Na into delta E by delta T at constant volume, right? Now we know this, the average energy E is related with the partition function, that is 1 by q del q by del beta at constant volume. Okay, okay. Now okay, so now what we can do, so we have been asked to only calculate the vibrational contribution, so that's why we have written the suffix v here. V means the vibrational partition, vibrational energy and vibration partition function. So we know uh, for vibrational case, the qv looks like this, 1 by 1 minus e to the power minus beta e, right? The vibrational partition function. Now the ev, if you do the derivative of qv with respect to del beta, this whole term looks like this, 1 by 1 minus to the power beta e into minus 1 by 1 minus e to the power minus beta e whole square into minus beta e into minus e, right? Now this, so this will cancel, this will become plus e to the power minus beta e 1 minus e to the power minus beta e. This is the vibrational, average vibrational energy. Okay, now, okay, now you can further divided the whole thing by e to the power minus beta e, so then the whole expression looks like this, e by e to the power e to the power plus beta e minus 1. Okay, now E we know is hc nu tilde, right? The energy. If you substitute this here, so that will give you hc nu tilde by e to the power hc nu tilde by kt minus 1. Okay. Now we know, we have already familiar with the term of vibrational characteristics temperature, which expression is given by this theta v is the vibrational characteristics temperature, which is basically nothing but hc nu tilde by k. So we will now write this whole expression in terms of the characteristics vibrational temperature. So now the whole thing looks like this, k into theta v by e to the power theta v by t minus 1, right? Okay, so this theta v is nothing but the vibrational temperature. Now the ev, we got the expression of ev. Now from here the specific expression cvm is na into delta of ev by delta t at constant volume. So now if you do the derivative, so CVM now takes the form Na into K into theta V minus 1 into e to the power theta V by T minus 1 whole square into e to the power theta V by T into minus theta V by T square. Okay. We can write R equal to Na into K. We can know this expression. So for the whole expression now will be looks like CVM, the vibrational contribution will be R into theta V by T whole square e to the power theta V by T into e to the power theta V by T minus 1 whole square, right? Now so this is like will be the contribution that comes from the vibrational part. Okay, this is basically just the expression. Now so since we got the expression, just what we have to do, we have to just substitute all the values, right? After doing that, we'll be getting the value of the vibrational part of the specific heat. Okay, so for that, first what we need to calculate is the value of theta V, the characteristic vibrational temperature. So theta V is basically, we know that Hc nu tilde by K. Okay, now Hc value you already know, 6.626 and 10 to the minus 26. Light value, you know, 3 into 10 to the power 8. K we know, 1.38, 10 to the power, and nu tilde is given 2143 centimeter inverse. So we can write this unit as 10 since it's written in centimeter inverse. So if you calculate this all things, so theta V will be equal to 3083.3 Kelvin. Okay, so theta V by T would be 3083 by 3 by temperature is at 800 Kelvin, so it will be almost 3.85. Okay, the value of theta V by T. So now we have to substitute this value of theta V by T here. So CVM will be R into 3.85 square into e to the power 3.85 by e to the power 3.85 minus 1 whole square. R value we know, 3.85 square we know, e to the power 3.85 we already know. So if we calculate all of this quantity, we'll be getting the value of CVM equal to 0.3285. Okay, this is basically the value of the specific heat, molar specific heat, specific heat at constant volume due to the contribution of vibrational partition function. Okay, so so let me just briefly tell what we have done. So in the problem for carbon monoxide cat, we have been asked to calculate what is the contribution of the vibrational partition function into the heat capacity at constant volume, molar heat capacity at constant volume. So for that, what we have done, we have first write the expression of CV, the fundamental expression of CV, that is CV equal to del U by del T at constant volume. Now from here we know that since it's mentioned that you have to calculate the molar vibrational heat capacity, so as we know, the average number, like the average energy of each molecule, if it is this angular bracket T, then we can write for 1 mole of a CO molecule, the total internal energy U would be Na, that is the Avogadro number into the E. That gives you the total internal energy of 1 mole of CO gas. Okay. Now after doing that, we are substituting this thing here into the expression of CV. After that, we know that for the vibrational case, the average energy that is associated with the vibrational, the average energy due to the vibrational contribution of a molecule is equal to EV equal to 1 by Q. So this is our vibrational partition function QV, and the vibrational partition function looks like this. So from there we have calculated the EV. So EV we have now like write this whole expression of EV in terms of theta V, that is the characteristics vibrational temperature. So we have substitute this EV into the expression of CV. After doing the derivative, we got this expression of the CV here. Now from here, we just do some algebra and have simplified this whole thing by theta V by T. So theta V by T is basically act as a variable here in our equation. So what we have done, so in the problem everything is given, theta V, the nu tilde, temperature. So first what we have done, we have calculated the characteristics vibrational temperature theta V, that is 3083.3 Kelvin. So and T is given, so theta V by T we have calculated, and after that we have substituted that value into this equation. After doing that, we got this value of specific heat at constant volume, molar specific heat at constant volume. So this, the unit is would be like this, joule per Kelvin inverse per mole inverse, right? Since it's molar specific heat. So basically the main thing is this. So how we are getting this expression of vibrational molar heat capacity related with the characteristics vibrational temperature and the temperature of the experiment. So this expression is the important thing to derive here. After that, just you have to put the values accordingly in order to get the specific value of specific heat. Okay. Now we have asked to calculate the fraction of molecule in the weak vibrational state. Okay. Fraction of molecules at weak vibrational state. Okay. So for that, we know. So in order to calculate the fraction, we know since this whole thing is happening at equilibrium, so we just have to use the Boltzmann distribution, right, in order to get the fraction. So vibrational, according to the Boltzmann distribution function Pi, the fraction of molecules at the state in the state I is Ni by N equal to e to the power minus beta Ei by Q. This is the partition function. So and since here V is a vibration, so since here we have asked to calculate the vibrational state, so that means that Fv, so at V vibrational state, the fraction we are writing as Fv equal to e to the power minus beta Ev by Q. Q is nothing but 1 by e to the power 1 minus e to the power minus beta Hc nu tilde, right? That is the partition function, total partition function. Okay. So now if you substitute this Q here, QV more specifically, since all of these things are related to the vibrational energy state, so Fv is equal to e to the power minus beta Ev by 1 by 1 minus e to the power beta Hc nu tilde. It would be e to the power minus beta So for the new vth energy state, ev will be equal to v into hc nu tilde, right? So v into hc nu tilde into 1 minus e to the power beta hc nu tilde. Okay, so that is basically the expression of the fraction of molecule at the energy vth energy state. So from here, if v equal to 0, you have to just put 0 here into the expression. F0, you will be getting some value for v equal to 0. For similarly for v equal to 1, you will be getting f1. So all these values of nu tilde and everything is given. So just substitute all of the value and put v equal to 0, 1, 2, the energy state that you are interested in. Just put the value of the number of that particular energy state, and after doing that you will be getting the fraction of molecule at that particular energy state. Okay, so this is a quite straightforward. The next problem is quite straightforward, but for the first problem, this is the important thing. So here you have to first derive how the vibrational specific heat is related with the other vibrational parameters, okay, and variables. That relation is basically the important thing here. So after that, just you have to substitute the values. Okay, so this problem is now done. Next we will do another problem. Okay, okay. So problem number 2, for into at T equal to 1000 Kelvin, calculate the ratio of the number of molecules in the state. So state A has nu equal to 0 and j equal to 3. So state A has it's v equal to 0. State B has v equal to 1 and j equal to 1. And for this NO molecule, other constants are given. So the vibrational frequency nu is 7.06 into 10 to the power 13 second inverse. The moment of inertia I is given also 1.407 into 10 to the power minus 46 kg into meter square. Okay, so what basically asked in the problem is that for a NO molecule, so N2 molecule, so N2 molecule looks like this linear molecule. So here uh, for T equal to 1000 Kelvin, um, there are two states of this N2 molecules are given. One at state A. So state A is that where the molecule is at vibrational state V equal to 0 and rotational state J equal to 3. And state B is the vibrational state equal to 1 and the rotational state also equal to 1. So for these two different states at a fixed temperature T equal to 1000 Kelvin, we have to calculate the ratio of the numbers of molecule. Okay, for these two different states, state A and state B. So for that, what we can do is that so vibrational energy level is given by EV equal to V plus half H nu. Rotational energy is given by EJ equal to J into J plus 1 into H square by 8 pi square I. Okay, and these are the vibrational and rotational energy levels, right? Now you have to basically ask to calculate the ratio of the population, ratio of the population. So two states are here, A which has the vibrational state equal to 0 and rotational equal to 3, and B is vibrational is 1 and rotational is also 1. For state A and B, you have to calculate the difference in their population ratio. So Na is the molecules in state A, Nb is the molecule in state B. Na by Nb is equal to Gza by Gzb is basically the degeneracy of both these two levels is equal to exponential e to the power minus Ea minus Eb by kt, right? This would be basically the population. So now we have to calculate all of this thing, this what is this called, this degeneracy, and as well as the part, yeah, what is this called, difference in the energy. Okay, so first is um, the energy state. Okay, so total energy E is basically EV plus EJ, right? So that is V plus half plus H nu plus J into J plus 1 into H square by 8 pi square I. So at energy state, all of these other constant H, I, K, C, all these things you already knew, right? So first we have to do is for state A. For state A, EA is equal to, so new V, sorry, this is V. So V is basically 0 and J equal to 3. So it would be 0 plus half into 6.626 into 10 to the power minus 34 into nu is already given 7.06 into 10 to the power 13 into 10 to the power 13, that is comes from the vibrational part. Rotational part, j equal to 3, so 3 into 3 plus 1 into, so for vibrational case the energy would be 3 into 3 plus 1, 3 plus 1 by this whole thing, a square by 8 pi square I. So after doing all this calculation, EA would be something like this: 2.3390 into 10 to the power minus 20 joule, plus for the, this is the vibrational. For the rotational term, the energy would be 4.474, sorry 4.7 into the minus 22 joule. Okay, for state B, EB would be equal to 1 plus half into H nu, plus for B, J is also equal to 1, so 1 into 1 plus 1 H square by 8 pi square I. Similarly here, if you do the calculation, the first term would be 7.0170 into 10 to the power minus 20 plus 7.904 into 10 to the power minus 23. Okay, so we got EA and EB, right? Now you have to take the difference between EA and EB. So if you took the difference, EA minus EB will gives you minus 4.638 into 10 to the power minus 20 joule. Okay, the difference between A and B. Now we know that each state also has some degeneracy factor associated with it. So each state has degeneracy factor Gj equal to 2 into J plus 1, right? So now Na by Nb equal to Gza by Gzb into exponential Ea minus Eb by Kt. Okay, now here Gza is basically 2 into J, so 2 into J, so first case the J was 3, right? So 2 into 3, so 3 into 2, 6 plus 1, 7. And next case the J is equal to 1, so 2 into 1 plus 1, so 3 into exponential energy difference. You already know it's minus minus will become plus 4.638 into 10 to the minus 20 by Kt, 1.38 into 10 to the minus 23 into 1000. Temperature is mentioned into the problem, that is 1000 Kelvin. That's the basically Na by Nb. If you do calculate this Na by Nb, it will gives you 7 by 3 exponential. If we do this whole calculation inside this thing, 4.638 into 10 to the minus 20, the whole thing is divided by 1.38 into 10 to the minus 23 into 1000. So this basically gives you 3.36. Okay, 3.36. Okay, now 7 by 3 is almost 2.33 into, if you do this, 20 will give you 28.79, so it will give you 67.2 Na by Nb. So the population of 8th state will be 67, around 67 times higher than the population in bth state. Okay, so this is how, okay, you can calculate. Okay, so let me just briefly discuss what we have done in the problem. So for a nitrogen atom, so for 1000 Kelvin temperature, we have been asked to calculate the ratio of the number of molecules between two state. One is state A, which has the vibrational state V equal to 0 and rotational state J equal to 3, and for state B the vibrational state equal to 1 and the rotational state J equal to also 1. And here the nu, that is the vibrational modes, single vibrational modes, that is given, that frequency, that is 7.06 in 10 to the power 13, and the moment of inertia is also given. Now next, what we have to basically do is related with this formula. This is basically the population ratio of A and Bth state, Na by Nb, is basically equal to Gja by Gzb, the ratio of the partition function, into exponential Ea minus Eb, the energy difference between the 8th state and Bth state, by Kt, right? So now for the energy state A, that is the vibrational state V equal to 0 and the rotational state J equal to 3. For 8th state, first we have calculated the vibrational, and using the expression of the vibrational energy and rotational energy, we have calculated the energy at state A, that is given by this. Similarly, for state B, we have calculated the energy at state B. Next, here from this problem you can see we have to first calculate the difference between state A and state B. So Ea minus Eb we have calculated. Then we have substitute Ea minus Eb into this expression. After doing that, also we need the degeneracy also is important here. So since the rotational energy states are involved, so that means rotation energy states inherits this degeneracy, right? So so the inner, so for a jth rotational level, the degeneracy associated with it is Gj equal to 2j plus 1, right? So for j equal to, let's suppose 3, the first state, 8th state, it's 7, and for bth state it will be 3, right? So we have also substitute the degeneracy factors here, and previously we have already substitute the energy difference. Now just do the numerical calculation, and after doing that you are getting this population ratio Na by Nb. Here it is 67.2. Okay, so this is a problem we have done. Now we will do another problem. Okay, so let me write the next problem. Problem number 3. Calculate the standard molar entropy is not of carbon monoxide gas at T equal to 298.15 Kelvin, and P0 is 1 bar obviously since it's in standard case. So P naught, the value of pressure should be in 1 bar. Using the rigid rotor approximation, use the values, spectroscopic values basically. So rotational constant V value is given equal to 1.931 centimeter inverse. Vibrational wave number nu tilde is given 22143 centimeter inverse. The molar mass is given m equal to 28.01 gram per mole. Okay. 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 So these are the all things given. So since it's standard state, so pressure is 1 bar, temperature is given. So now the other constant, that is the Planck's constant, Boltzmann constant K, uh, uh, ideal gas constant, that constant is already, we already knew that constant's value, right? So let's now do the problem then. So here we know the expression of the entropy looks like this: S equal to U minus U0 by T plus K into ln Q. Q is the, this is the total partition function of the system. Now we can write for indistinguishable molecule. For, let's suppose these molecules for the time being is indistinguishable, since all the molecules are in a gas, in this gas system all the molecules are carbon monoxide, so they are basically identical, so you cannot distinguish basically among themselves. So indistinguishable condition, indistinguishable case, the Q equal to small q to the power n by n factorial, right? From here the entropy is equal to u minus u0 by t plus k into ln qn by n factorial, which is equal to u minus u0 by t into t plus k into ln q to the power n by k ln n factorial. Now from here, if you do the further derivation, then is equal to u minus u0 by t into min plus nk by ln q minus k into n ln n minus n. So now you can write, since we know na n equal to basically n into na. So if you substitute n into na here also here, so after doing that you will be getting u minus u0 by t in plus n into r, since na into k equal to r, right? So ln q minus nr ln n minus plus nr. Okay, now the u minus u0, that is the uh, internal energy, is basically this n by q. This expression already know, del q by del beta at constant volume. This is the expression of the internal energy u minus u0, right? Now you can further write it like this, minus n into delta ln q by delta beta at constant volume. Okay, since okay, so anyway, so you can also write in terms of t also. Like instead of writing it in terms of beta, you can write in terms of t also. In that case it would be plus n k t square into delta ln q delta t. If you write in terms of t, it will looks like this. It will look like this. So now the s will be simply equal to nkt into delta of ln q by delta t at constant volume plus nr into ln q minus nr into ln n plus nr. So here, as you can see, these two terms basically dependent on q. Okay, so whatever the contribution of rotational, vibrational, or translational partition function, that would be reflected in these two terms, right? So let's first consider, since N2 is a gas like this, so it's a kind of a linear gas, so it has both QT translational, QR rotational, and QV vibrational. For the time being, we are ignoring the electronic part. Okay, so first let's start with the translational part, right? So one thing also you can do, you can write this entropy expression in a more simpler way like this, nkt into delta of delta t into ln q. Just combining these first two terms, that will make things easier actually. Okay, so if you combine these two terms in a derivative, then it will looks like this, nr nkt. So nkt you can write further as nr, so this you can write as nr actually. So nr in plus nr minus nr into ln. Okay, this is the final expression of the entropy. So First, let's consider the translational case. Okay, so Qt is translational part. The translational part Qt is basically, we know, V by lambda Q, right? And lambda is a thermal wavelength that is given by H by root under 2 pi m kt. So Qt would be simply V by H cube into 2 pi m kt by 3 by 2. Okay, this is the expression of the translational partition function. Okay, now from the standard condition we know that P0 V0 equal to RT. So V0, this is basically standard condition, so V you can write as V0. Okay, so V0 is basically RT by P0. The advantage of writing the V0 like this is basically it's in standard condition, so we know the P0 and temperature is also mentioned, so we can calculate. So that is the reason we are writing the V0 in terms of T and P0. Okay, so Qt you can write it as uh, RT by P0. So RT by P0 into uh, 1 by H cube 2 pi m kt by 3 by 2, right? Now from here the ST, the translational contribution, ST is basically NR into del T into ln Qt, right? If you do that, it will gives you NR into to the power 5 by 2 into 2 pi m kt by 3 by 2 into RT by P0, whole thing is divided by Na by H cube. This is the expression of ST. Now if you substitute all of this thing here, you know all this thing, temperature uh, you know the temperature, you know the this all constant values, the mass, m, molar mass is also given, Na, R, everything you know. Just substitute it here, then you will got, then we will be getting the ST equal to something. Okay, the basically the contribution that comes from the entropy, translational entropy. Okay, next similar way we will do the vibrational part. Okay, first rotational part, sorry, rotational part. Okay, uh, so for the rotational part you can write it as SR. SR is similar way is equal to NR into del T of ln Q R by del T at constant volume. Okay, now QR, the rotational part is basically 1 by sigma HC beta B. Okay, so beta we know is KT, so KT into sigma HCB. This is the expression of QR. Now what you have to do, simply substitute this expression of QR here to the expression of SR. So SR would be simply, SR would be nr into del t of. Now one more thing is that this rotational case is only possible, we can only take this thing uh, only if theta r, that is the characteristic rotational temperature, that expression is given by hcb by k. So temperature of the experiment should be greater than equal by theta r. So under that condition only this is true. Okay. So since let's for the time being assume that this condition is true. So by considering that, so we have to substitute this expression of qr here into this equation of sr. Okay. So okay, so now it would be looks like sr equal to okay, sr equal to, yeah. So if you do the derivative both sides, so first it will give you, just take nr as common, nr into t by q delta q by del t, plus if you do the derivative again on t, it just gives you ln q, right? Now next is nr into, so q is already known as kt by sigma hcb, so that means t by q, if you substitute sigma hcb by kt into k by sigma hcb plus ln q. Next is nr equal to, so this thing will cancel, this thing will also cancel, so just 1 plus ln ln q. Qr also we also know, you can just substitute it here, kt, so this is rotational, qr. Okay, kt by sigma hc. Okay. Now so this is a fairly simple expression, right? So now what you have to do, just substitute, so everything you know, temperature and other things are basically constant, so just put it into this expression of sr, that will gives you the rotational contribution to the entropy. Last comes the vibrational contribution. Okay. So the vibrational contribution to the entropy is simply written by SV, that is nr into del t of t into ln of q vibrational, that is at constant volume, right? So now here the qv, the vibrational partition function is given by this expression 1 by 1 minus e to the power minus hc nu tilde by kt. This is basically the expression of qv, the vibrational partition function. Now if you took ln on the both sides, ln qv basically gives you minus ln of 1 by, so 1 by e to the power hc nu tilde by kt. Okay. Now from here, if you took a, put sv equal to nr into del t of t into ln qv, so minus ln of 1 minus e to the power hc nu tilde by kt. So this whole thing will be inside the derivative with respect to the t. So sv equal to nr into okay. So now you have to basically do this whole derivative. Okay. So first, okay, yeah. So first, let's do the derivative. Let's take t as fixed first. If you do the derivative onto this ln big ln term, that gives you minus 1 by 1 minus e to the power minus hc nu tilde by kt into e to the power minus hc nu tilde by kt into 8c nu tilde by kt square, right? Next derivative, just take if you just have to take the long term as constant and derivative with respect to the t of t, and that gives you, so minus minus will become plus, so this gives you ln of 1 minus e to the power 8c nu tilde by kt only, right? Okay, so we got fairly expression of, let me just read out in a much more cleaner way, nr into hc nu tilde by kt into e to the power hc nu tilde by kt by 1 minus e to the power hc nu tilde by kt minus ln of 1 minus to the power hc nu tilde by kt. Now now so we got the expression of the vibrational partition function sb. Now what we have to do, let's calculate hc nu tilde by kt. Okay, so here in order to calculate, because you can see this whole thing is basically written by taking hc nu tilde by kt as a variable, right? So just you know all these things, right? The h, the c, the constants, the nu tilde, the kt, all these terms, constant variables are given. So just calculate this and substitute here. So basically that gives you some value of sv, right? So you got st, you got sr, and you got the sv. Now if you substitute all of this thing here, so that gives you the total entropy. So let me write it. Total entropy is basically S is equal to, so the total entropy looks like this: St plus Sr plus Sv plus Nr into minus Nr ln n. Okay, so translational part got Nr into del t qt, sorry, ln qt. So this is basically coming like this. So uh, the whole thing is the at first the equation looks like this, like, right? S equal to nr into del t ln q by del t at constant volume plus nr minus nr into ln n. Now from here, if you can write q as translation, rotation and vibration, multiplication of all these three partition function gives you the total partition function. So into nr into del t of t into, so ln of q gives you ln qt plus ln qr plus ln qv, right? This whole thing will be at constant volume v plus nr minus nr into ln n. Now here s would be nr into del t of ln qt by del t plus del t. This whole thing would be on inside the derivative, ln qr by del t plus del t of t into ln qv by del t. This whole thing will be constant volume plus nr minus nr by ln n. So this thing gives you, the first term gives you sr st, the second term gives you sr, and the third term gives you sv plus nr minus nr into ln n. So this is the value of the total entropy S, which basically includes SR, ST and SV, rotation, translation and vibrational terms, right? Okay, this is how you should calculate the total entropy of the system. So here all of this individual entropy terms you can calculate. It's basically easy. So all of their expressions is given here. Okay, so let's here for the rotational, for the translational, this is the expression. For rotational, this is the expression, and for the vibrational, this is the expression. Okay, all of this expression you can numerically calculate by putting the constant that is supplied into the problem. That is the easy part. After that, just add all this entropy, then you will get the total entropy. Yes, okay. So right now, so today what we have discussed, so we have basically started from like the change in Gibbs free energy. So we know the change in Gibbs free energy basically gives you the equilibrium constant K, but the change in Gibbs free energy also depends upon the change in enthalpy and the entropy change, right? In a reaction you can calculate those things, right? Entropy change, enthalpy change, and from there just by just using this relation we have shown here that using this relation you can calculate the population ratio of product and reactant, and from there you can basically calculate the equilibrium constant K that depends upon this partition function and the changes and the energy difference between the 0 point energy. For that, next we have do some problems calculating specific heat at a particular temperature due to the vibrational contribution. Next we have also calculated the energy difference, the population difference between two energy states, how to calculate, and lastly we have calculated the entropy, like the rotational, translational, vibrational entropy, how to calculate for a system in standard state, that we have done. So for today's class that's it. So let me stop the recording.